Hello everyone and welcome to the fifth tutorial of this video series. And today we're going to look at the Python programming language into more detail. We'd just like to give you an overview of logic, which forms the basis of any programming language. And in the broader sense, logic is just the study of formal reasoning, which helps us then to define the logical syntax for computers to correctly compile code, and obviously which governs what are valid expressions in this language, etc., etc. So when it comes to defining a language, I would just like us to take a step back in terms of what we already know, which I sometimes refer to as a Shakespearean paradigm. In the Shakespearean paradigm, we normally break up sentences in terms of verbs, nouns, adjectives, etc. However, in a mathematical or a programming language, we break up sentences in a bit of a different way in terms of propositions and connectives and the likes. In this classical Greek approach of constructing a language or defining a language, we are more interested in the substance of the message that we are trying to convey. We are interested in things such as the expressive power of the language and whether we can actually say with meaning what we intend to say. We want to avoid ambiguity at all costs, and we want to make sure that what we say is what we mean and what we mean is what we say. In order for us to capture the exact meaning of a sentence, we must look at the definitions of connectives. This is something we are quite familiar with in a natural language setting when we use words like and, or, not, if, then, which I've tabulated below. We also restrict our attention to true statements, since false statements in a mathematical sense is not really useful. We can use Boolean values, true or false, to build our interpretation of negation to mean that the truth assignment or the valuation of not true returns false, and the truth assignment or valuation of not false is true. In the case of conjunction, the interpretation is that the sentence is true if both constituents or propositions that make up the sentence is true, and false otherwise. In the case of disjunction, the sentence is true if either of the constituents or propositions are true and false otherwise. We will look at implication a bit later, but for now, let us go through what we mean by each of the connectives above in terms of Python syntax. So to elaborate what I've just explained in the above table, we're going to look at each of these connectives in an isolated manner. So the interpretation of the negation is that if you're given a proposition P, which could be either true or false, then the negation of P would return the opposite Boolean value. So to illustrate this in the Python syntax, I've just introduced a Boolean variable x, which I set equals to true, and then I will print to the screen not x, and that should return, as expected, false. If I change the Boolean variable value to false, then print the value not x, I would expect to get the value true. In this table, I am given propositions P and Q and all possible combinations of Boolean values. True, true, false, false, true, false, true, false. That just means I'm going to use these propositions and combine them in a way using the conjunctive and then evaluate the entire sentence based on these two constituents. When two propositions are true, then their conjunction is also true. If either of them are false, then the value is false. Okay, so to illustrate that in the sense of the Python programming syntax, I have two variables, in which case I've set both of them to true initially. So x is true or y is true, and so I'm going to print to the screen that I want to return x and y, and you should expect that the value is true. Okay, if either of the two is false, so if I change this to false, then the result should also be false. If the first variable is false, that should be false, and if both of them are false, I should also expect a value of false. Next, we're going to look at the disjunction of two propositions P and Q, in which case you can see that if any of these two are true, then the entire sentence evaluates to true, and only if both of these are false, then we should expect a value of false. So all I've done here is I've assigned Boolean variable x, y true in the first case, which returns true. In the second case, I get true or false, returns true. In the third case, false or true returns true, but false or false returns false. Next, we are going to look at the implication connective, which is defined by this truth table and may seem peculiar in the second line and the third line, which I will elaborate a little bit on for clarity. So the interesting thing to note is that if the first proposition is true and the second is false, then the entire sentence should always evaluate to false, since if the conclusion is false, automatically the entire sentence should be false, which that makes sense. But in the third row, you can see that the first proposition is false and the second is true, then the entire statement results to true. So that may seem counterintuitive to a lot of people, but to explain why this is true, just imagine that you have a statement in which the condition of the statement, that means the first proposition, is false. Then it is a matter of fact that the entire sentence should result to true, since anything can result from a false condition. So for example, if I had said that if pigs can fly, then I shall be king, that is the classical example for why the statement holds true, then that makes sense, because from a false assumption, I can actually conclude that anything is true. Another example that I can come up with that I recently thought about is the little riddle that if 5 divided by 2 is 3, well, then what is 10 divided by 2? And so a lot of people, what they would go and do to try and answer this riddle is that they would want to go and compute the values in this problem. They would say something like 5 divided by 2 is 3, so then 10 divided by 2 should be double that. And in fact, then the answer according to them in their mind should be 6, but that is actually completely flawed, because the real answer is that anything can then be true, because the assumption that you're working from, that 5 divided by 2 is equals to 3, is not true to start with. And so the answer is that anything can actually be true. So that problem comes down to this truth table. All right, so you might have to want to go and sit down and think about this table for a little bit, and try and make sure that you really wrap your mind around this statement 100%. Okay, so the next thing that I would like to mention is just a couple of examples of how exactly this statement is used, and where we actually see these statements coming up. So as an example, I'm just going to say that, and I hope nobody takes offense in the statement, that if you eat McDonald's, right, then you will become fat. And so our connective is if then, and the condition is that you eat McDonald's, and the conclusion of that sentence is that you will become fat. And this is an example of how an implication statement is structured. Okay, so keep that in mind while you try and understand this truth table. Before we go ahead and define the implication connective in terms of the Python programming language, I would just like to mention a few words about adequacy, which we've already kind of discussed here in the first cell of this Python Jupyter notebook. And what it comes down to is that we want to keep our language to a minimal, having as few as possible symbols necessary while maintaining expressive power. And what that really means to say is that a set of connective is adequate if all other connectives can be expressed in terms of the connectives of that set. So for example, this set, negation together with implication or not and if then, is quite sufficient for being able to say everything that we need to say. We don't need to necessarily use or and as connectives in our language. We can actually just use these two. But that may be overkill to try and simplify our language too much, because it's really restrictive. It makes the code hard to read. But the idea that I'm trying to convey is that it is quite possible to do this. And the reason I'm saying that is because right now I actually want to go ahead and define the implication operator in terms of our known connectives that we've just discussed a couple of minutes ago. So the implication operator that I defined here is defined in terms of not and or. And we will look at logical equivalence in the same setting, because what I'm trying to say here is that this new expression here, not x or y negated, returns the same truth table as what we've defined over here in implication. And you can go and do that by hand and compute the truth values for the last column, for the sentence, to make sure that it always returns the same values: true, false, true, true. Right? So here I've defined, using the Python programming syntax, the implication operator. I've come up with my own operator, and I'm going to actually go call that function with the truth values true, true. That's true, false, in which case we should expect the value to be false. If the first one is false, we should expect the value to be true. And in the last case, if both of them are false, we should still expect a value of true. So basically what I'm saying is that I've defined the implication, that means the arrow, this if then connective in our logical language. We have defined that in terms of not and or. And so what I would like you to do as an exercise, I would like you to go and do something similar to what we've done over here. I want you to define implication in terms of negation, that means not, and conjunction and. I've defined my implication operator in terms of not and or, and I want you to go and look at how can you do the same thing in terms of not and then present this in a truth table to make sure that those two expressions that you've come up with are logically equivalent and do produce the same truth value. Okay, so then you can write a little Python function to verify your results, and by verifying I mean go and print these truth values for combining these propositions with the implication operator. And so that concludes our tutorial, and I hope to see you in the next one.